Welcome to another lecture in the course on 3G, 4G wireless communication systems. In the last lecture, we were discussing or completing our discussion on delay spread and frequency selective channels. Specifically, we said if the channel is frequency selective, that is, if the signal bandwidth is greater than the coherence bandwidth, then in time domain it means that the delay spread is greater than the symbol time. Hence, the channel results in intersymbol interference, which causes distortion at the receiver. So, frequency selectivity in the frequency domain corresponds to intersymbol interference in the time domain. We also introduced the notion of Doppler resulting from a moving mobile, that is, as the mobile moves with a velocity v, the received carrier frequency changes. In particular, that is given by this relation f c plus v cos theta over c times f c, where v cos theta over c, f c is the Doppler shift, v is the velocity of mobile and theta is the angle of the velocity with the line joining the base station and the mobile. We said this Doppler or this velocity of the mobile results in a time varying delay. Previously, we had a delay fixed, which is tau I, but now because the mobile is moving, the delay itself is changing, which means now the channel itself is changing because the delay is changing. Hence, now Doppler results in a time varying or also a time selective channel. This is what we said in the last lecture. And finally, we said the time of significant change of the channel is t equals 1 by 4 f d, where f d is the Doppler frequency. The t for change is 1 over 4 f d, which is t c, the coherence time, which is that interval of time over which the channel is approximately constant. That is, the channel is changing, it is changing from time to time, but we can assume that it is approximately constant over one coherence time interval, which corresponds to 1 over 4 f d. Also observe that f d is proportional to the velocity, which means if the velocity is high, f d is high, which means the coherence time t c, which is 1 over 4 f d, is low. So, as the velocity is increasing, the coherence time is decreasing, which is intuitive, because if the vehicle is or the mobile terminal is moving faster and faster, then the channel is also changing faster and faster, which means the coherence time is lower and lower. All right. So, with that notion, let us start today's discussion. That coherence time. Let us start today's discussion. Let us refine this notion of coherence time. Coherence time T c equals 1 over 4 f d. I can also write this as 1 over 2 b d, where b d equals 2 f d equals the Doppler spread. I will define a new quantity 2 f d defined as the Doppler spread. That is, twice f d is Doppler spread. Hence, the coherence time T c is 1 over 2 b d. Let me write that clearly. Coherence time equals 1 over twice the Doppler spread of the channel, which is B D. Okay. Let us do an example to understand this better. Let us do an example of a 3G, 4G wireless communication system. Let us go back to our earlier example where there was a vehicle or there was a person in a vehicle which was moving at 60 miles per hour, that is, vehicle at 60 miles per hour moving directly towards the base station at carrier frequency f c equals 1850 megahertz, or in other words 1850 megahertz is the same as 1.8 gigahertz or 1.85 gigahertz. Now, we want to find out what is the coherence time. So, want to find out what is the question. Question is, what is the coherence time of this channel. Let us compute that. We computed earlier that for a vehicle moving at 60 miles per hour in the direction of the base station at carrier frequency 1.8 gigahertz, the Doppler shift FD is nothing but 165 hertz. The Doppler shift is 165 hertz, which means the Doppler spread BD equals twice FD equals 2 into 165 equals 330 hertz. That is the Doppler spread. This is nothing but the Doppler spread, that is the Doppler spread of a vehicle moving at 60 miles per hour with a person sitting in it, or a mobile moving at 60 miles per hour directly towards the base station at and communicating at a carrier frequency of 1.85 gigahertz is 330 hertz. Hence, the coherence time TC equals 1 over 2 BD equals 1 over 2 into 330 hertz. This is also essentially 0.0015 seconds, or I can write the same thing as 1.5 milliseconds. Hence, the coherence time is 1.5 milliseconds. Since let me write this down here, TC is the coherence time equals 1.5 milliseconds. So, what does this mean? This means that when you are moving at 60 miles per hour towards the base station, roughly the period of time over which the channel is constant can be assumed to be 1.5 milliseconds. After 1.5 millisecond, the channel changes to something different. That is, if I am looking at the fading coefficient H, in one period of 1.5 milliseconds is approximately constant. In the next period, it has changed to some value, a different value, which is L H tilde, and so on. Alright, so that is the importance of the channel coherence time, and you can also see that this coherence time is approximately of the order of milliseconds. So, let me write down that property also here. In real wireless channels or in practical wireless channels, coherence time TC approximately of the order of milliseconds. So, look at this. What I am saying is, just like we said, in practical outdoor wireless channels, delay spreads are approximately of microsecond duration. Coherence time, which is another important parameter which is related to how fast the channel is varying, is roughly of the order of milliseconds. So, these are two important quantities that one needs to remember. One is the delay spread, which is microseconds, one is the coherence time, which is of the order of milliseconds. Alright, and both of these are fundamentally different. One is the delay spread is related to that interval of time over which signal energy is arriving, while coherence time is related to the time duration over which the channel is constant. These are fundamentally different quantities, one is not related to another. So, I urge you again to revise this concept so that you understand it clearly. Alright, again to point out, coherence time is related to the Doppler spread, while the coherence bandwidth is related to the delay spread. So, these two, so let me write them down here, BC and coherence bandwidth and the delay spread sigma tau are related to each other. This is coherence bandwidth and the delay spread are related to each other, and the Doppler spread and coherence time, these two are related to each other. Doppler spread and coherence time. I think it is essential to point out that sometimes it is confusing to think that because the coherence word applies in both the bandwidth and the coherence time, it is commonly, it's confusing sometimes when people relate coherence bandwidth to coherence time. However, coherence bandwidth is related to delay spread and Doppler spread is related to coherence time. It is important to understand these two concepts very clearly. So, I urge you again to revise this discussion in this lecture in the past lecture, so that you understand these concepts clearly. All right. Now, let us go into a more detailed analysis of the Doppler fading. Let us compute what is known as the Doppler spectrum. The Doppler spectrum. For this, I will need what is known as the correlation function of the channel. So, first I want to compute the Doppler spectrum, because gives me a better idea, it gives me a more clearer idea of how fast or how slow is the channel varying with respect to time. So, I want to compute the Doppler spectrum. So, because it gives intuition into the rate of change of the wireless, of the 3G 4G wireless channel. So, if you want to analyze this rate of change in greater detail, I want to compute something known as the Doppler spectrum. Now, for this I will embark on a related I will go on a related discussion. Let us consider two random variables, x comma y. We know that the correlation defined as expected x into y conjugate, this is the correlation. This is a measure of how similar or dissimilar these random variables are. This is expected x y conjugate, is also known as the correlation. If the correlation is high, let me write them here. If correlation between x comma y is high, then x and y are similar, then x comma y are similar. All right. So, if there are two random variables x and y, I compute the correlation between x and y given by expected x y conjugate. If the correlation is high, then x and y are similar, that is, they take values, high values and low values, roughly related to each other. However, if x and y the correlation is low, then it means x and y have no bearing on each other. What the value that x takes is not related to the value that y takes. So, correlation is an important property of random variables. Again, please revise this concept from your knowledge of random process and probability. All right. Now, so correlation indicates how similar or how dissimilar two random variables are. Now, what I want to do is I want to compute the following correlation. I want to compute, we know that AI of t is the channel coefficient at time t. AI of t is the channel coefficient at time t of the ith path, and we also have an expression for AI of t. AI of t is nothing but AI, which is the attenuation, times e power minus j 2 pi f tau I times e power j 2 pi f d t. We said AIT, we earlier derived this expression, AIT is AI, the attenuation, times e power minus j 2 pi f tau I, where tau I is the initial delay, times e power j 2 pi f dt. We said this is the time varying phase factor. This is the time varying phase factor. This results in, this is what results in the time varying nature of the channel. This results in time varying wireless channel. All right. Now, what I want to compute is I want to compute the time correlation of this channel as follows. I will compute the quantity expected AI t, AI conjugate t plus delta t, that is I am taking AI of t, that is at a given time I am looking at the channel coefficient of the ith path. I am computing its correlation with ai conjugate t plus delta t, which is the coefficient delta t later. So, this is coefficient, this is the coefficient delta t later. Now, if this correlation is high, this means AIT and AIT plus delta t have high correlation, which means the channel variation from t to delta t is lower. Alright. However, if AIT correlated with AI conjugate t plus delta t is low, it means the random variables are dissimilar, hence the channel has changed significantly from t to t plus delta t. So, I will summarize that thought here. If correlation between AIT and AIT plus delta t is high, this implies channel has not, remember, has not changed significantly from t to t plus delta t. So, if the correlation between AIT and AIT plus delta t is high, the channel has not significantly changed from t to t plus delta t, because AIT and AIT plus delta t are similar. However, if the correlation between them is low, then the channel has, then AIT and AIT plus delta t are different, hence the channel has changed significantly from AIT, from t to t plus delta t. Alright. Now, let us compute this correlation, so that the correlation as a function of delta t gives me an idea of how fast the channel is varying, alright, as we just described before. So, now AIT is nothing but AI e power minus j 2 pi f tau I e power j 2 pi f d t, and AI of t plus delta t equals AI e power minus j 2 pi f d tau I e power j 2 pi f d t plus delta t. What I have done here is I have written AI of t and AI of t plus delta t. Now, I need to compute AIT into AI conjugate t plus delta t and take the expected value. So, I will write this as the correlation coefficient psi of delta t as expected AIT into AI conjugate t plus delta t, which if I take this product AI into AI conjugate, that gives me magnitude AI square into e power minus j 2 pi f tau I f d tau I into e power minus j 2 pi f d tau I conjugate, that gives me 1 into e power j 2 pi f d t into e power minus j 2 pi f d t plus delta t, that gives me e power minus j 2 pi f d delta t. So, psi of delta t, which is the correlation between AIT and AIT plus delta t, is expected magnitude AI square 1 into e power minus j 2 pi f d delta t. I will assume that this path is normalized to unit power, that is, let us take this power out of the picture by normalizing, because this power depends on the transmitted signal power and so on. So, let us normalize this to unit power by taking power and then take power out of the picture, and now this becomes the correlation coefficient, now becomes psi delta t is expected e to the power of minus j 2 pi f d delta t. This is the correlation coefficient. Remember, we still have to take the expected value, we still have to take the expected value over f d over f d, that is important. All right. So, I will write this as follows. I will write this as expected e to the power of minus j 2 pi and Fd I will write as Fc V over C cosine theta into delta t. I am writing, I am not doing anything extra complicated, I am simply writing Fd as Fc V over C cosine theta, where V is the velocity, theta is the angle. This is nothing but Fd, I am substituting Fd in the relation above. That gives me psi of delta t. Look at this, Fc V over C is nothing but the maximum Doppler shift that corresponds to Fc V over C when theta equals 0. This is the maximum Doppler shift, that is Fc V over C, which is when the mobile is directly moving towards the base station or away from the base station. So, I will write this as expected e to the power of minus j 2 pi Fd max cosine theta over delta t, where Fd max equals Fc V over C, and this is the maximum Doppler, this is the maximum Doppler shift. Now, I have to take the expected over theta, because remember theta is still unknown, because theta we said lies between 0 and pi depending on if the mobile, let us say this is the mobile, this is the base station, this angle is theta. So, theta can lie between 0 and pi. So, theta is a random quantity depending on the direction of the velocity and the line joining the mobile station and base station. Theta can lie between 0 and pi, hence we will assume theta as uniformly distributed between 0 and pi. This is a reasonable assumption to make, because in a mobile cellular network the direction of velocity at any point is random. So, each user, each mobile station is moving randomly in one particular direction. That direction can be assumed to be uniformly distributed between 0 and pi. Now, I can take the expected value of this correlation coefficient psi of delta t. The average correlation is nothing but 0 to pi 1 over pi e power minus j 2 pi f d max delta t cosine theta de theta. Look at this, the correlation coefficient is a function of theta, that is e power minus j 2 pi f d max delta t cosine theta. I am saying theta is distributed uniformly in 0 to pi. So, I am multiplying by 1 over pi, that is the distribution, and averaging it from 0 to pi by integrating this. Hence, this is nothing but, and hence this is the correlation. Now, I am going to simplify this integral. This is e power j some constant times cos theta times d theta. This is nothing but the Bessel function. So, this value is j 0 to pi f d max times delta t. So, I have derived the structure of the correlation, and that correlation is given by, as a function of delta t, is given as j 0 2 pi f d max delta t, where j 0 is the Bessel function of 0th order. So, we have now a very interesting relation. We said the correlation coefficient between the channel at t and t plus delta t can be derived as j 0 2 pi f d max, the maximum Doppler shift corresponding to velocity v, times delta t, where j 0 is the Bessel function of the 0th order. Hence, this gives me the correlation as a function of time. Let me show you a plot of this. For instance, if we go here in this I have plotted the correlation. Before that, let me do a minor simplification to this. So, this is j 0. So, psi of delta t is j 0 2 pi f d max of delta t. This can also be written as J0 2 pi. Remember 1 over 4 d, 1 over 4 t coherence, that is 1 over 4 times coherence time is f d max. So, f d max I will write as 1 over 4 T c times delta t. I can also write this as J0 pi over 2 delta t over T c. Alright, so this correlation time or this correlation function can also be expressed as J0 pi over 2 delta t over T c, that is correlation at the channel delta t away. Now, let us go to the plot. I have plotted here J0 pi by 2 delta t over T c. You can see as delta t increases, it is decreasing, but it is the Bessel function. So, it decreases in a cyclic kind of way. So, if you look at this, this means at delta t equals 5 T c. Let us look at this point, delta t equals 5 T c. This is delta t equals 5 T c, that is at a time duration, that is 5 coherence times away, the correlation is only 0.2, which means the correlation is low. So, the channel has changed significantly. In fact, if you look at delta t equals T c, somewhere around this point, delta t equals T c, you will find the correlation is 0.5. This is at delta t equals T c, and hence we are saying that at a time lag, that is T c away, the correlation between AIT and AIT plus delta t is only 0.5. So, the channel has kind of changed significantly from AIT, since the correlation is low. Any correlation less than 0.5 can be considered as a low correlation. If two random variables are significantly correlated, then the correlation has to be approximately close to 1, 0.9, 0.8, so on and so forth, which means at delta t equals T c, the correlation is 0.5, hence the channel is changed significantly, and that also forms the basis or the rationale for our earlier reason argument that in after one coherence period T c, the channel changes significantly. Now, let us go back to the lecture and again let us analyze this further. So, now I have the correlation function. I want to compute what is known as, now I can, from the correlation function I can compute the Doppler spectrum. The Doppler spectrum SH of f of a channel is given as minus infinity to infinity. It is given as the Fourier transform of the correlation function. So, I take the correlation function psi of delta t, I take its Fourier transform. Remember, the Fourier transform is with respect to delta t, not with respect to t, d delta t. This is the Fourier transform. Now, psi of delta t, we know it is a Bessel function. So, this is minus infinity to infinity, this is J naught 2 pi f d max times delta t times e to the power of minus j 2 pi f delta t dt. This can be given, this is given by an expression. This Fourier transform of the Bessel function is a standard known function that is given by an inverted U shaped function. So, let me write that down, that is SH of f is nothing but 1 over pi f d max rect, that is the rectangular function, f over 2 f d divided by 1 over square root of 1 minus f over f d square. All right. So, now we have derived the Doppler spectrum. This is what? This is the Doppler spectrum, and we are saying that is the Doppler, that is Fourier transform of the correlation function, which in our case is a Bessel function, which can be written as 1 over pi f d rect f over f 2 f d 1 minus f over f d. The rect function is given as follows: the rectangular x equals 1 if mod x less than equal to half, 0 otherwise So, the rectangular function looks as follows, that is simply between minus half and half, it is 1. So, this is how the rectangular function looks, and now let me approximately plot this spectrum, Doppler spectrum. So, a plot of Doppler spectrum that looks as follows. Now, look at this Doppler spectrum at f equals f d, this is f by f d is 1. So, 1 minus 1 is 0, which means this shoots up to infinity, and for f greater than f d this is not defined, because then this 1 minus f over f d is less than 0, hence the square root is not defined, hence it exists only for f between minus f d, and towards f d it shoots up to 0. This Doppler spectrum is given as follows, it is symmetric about f d and it looks like this. At f d and minus f d it shoots up to infinity, alright. It is an inverted U, it is increasing and limited between minus f d and f d, hence at f d and minus f d it shoots up to infinity, hence this is a U shaped spectrum, this is a U shape spectrum. This also has a name, this is very popular in the context of 3G, 4G wireless communications, even 2G wireless communications. This is known as the Jakes spectrum. This model is known as the Jakes model of a wireless communication channel. This spectrum is known as the Jakes spectrum, and look at this, look at the spread of this. This spread between minus f d is nothing but 2 f d, which is nothing but b d, the Doppler spread that we defined earlier. So, the Doppler spread is nothing but the spread of the Doppler spectrum. So, first thing is that this inverted U, which shoots up to infinity at minus f d and f d, is the standard Jakes spectrum as part of the Jakes model, and this has a Doppler spread of 2 f d, which is the b d, that is the Doppler spread that we defined earlier. Hence, we can now write Doppler spread is nothing but spread of the Doppler spread is nothing but the spread of the Doppler spectrum. As we have seen, this is a Doppler spectrum, the spread is 2 f d between minus f d and f d. Alright, so the Doppler spread is the spread of the Doppler spectrum, hence the Doppler spectrum gives us an idea of how fast the channel is varying. If you want to get an intuitive feel of how fast the channel is varying, we compute the correlation function. From that we compute the Fourier transform, which is the Doppler spread. This Doppler spread, you can measure the bandwidth of the Doppler spectrum, that gives you the Doppler spread, and 1 or twice the Doppler spread is the coherence time, which gives us an idea of how the channel is varying. This is the complete procedure to compute the coherence time of any given wireless channel statistically, right. So, this is a very important concept, the concept of Doppler spectrum. Now, what are the implications of coherence time? Let us try to understand what are the implications. Remember, channel is changing, it's constant for coherence time, and channel is changing from coherence time to coherence time. Hence, the channel, if you want to know about the channel, you need to measure it at least once every coherence time. Hence, to get knowledge of the channel, it needs to be measured at least once every coherence time. Let me write that over here. Hence, to get knowledge of the channel, it needs to be measured. This is the key word here, measured at least once every it needs to be measured at least once every coherence time. Why do we need to measure it once every coherence time? Look at this, we said our channel received signal y t is given as y t equals h times x t plus some noise, right, y t equals h times x t plus some noise. Now, let me assume that the noise is insignificant, that is the noise is small. So, I will erase this. So, y t is approximately h of x t. Now, if I want to recover the transmitted signal x t at the receiver, that is if I want to recover x hat of t, what do I need to do? I need to take y t, that is the received signal, and divide it by h, which means x hat of t is 1 over h y t. Alright. So, I need to take the received signal and divide it by h to get back my h t. What am I doing here? Here I am dividing by 1 over h, which is also known as channel inversion. So, I am inverting the channel. Because h is multiplied with the channel, all right, h is the fading coefficient which is sort of corrupting the signal. I need to invert this h by 1 over h, multiplying it with by t, that gives me x t. Now, to do this I need knowledge of h, which is the channel coefficient. So, I need knowledge of h. Why I need knowledge of h? I need knowledge of h for detection of x t. Hence, h needs to be measured at the receiver. This process of measuring h is a very standard procedure in 3G wireless, 4G wireless communications. It has a specific name. This procedure has a specific name. This is known as channel estimation. Hence, measuring or in fact estimating, the technical word is estimating the channel coefficient h is known as channel and channel estimation is a key procedure in every 3G, 4G wireless communication system. It is a very critical aspect of a 3G, 4G wireless communication system, because as we saw, we need h for detecting the transmitted signal. Hence, channel estimation is a key procedure for every 3G, 4G wireless communication system. So, now a pertinent question to ask is, how is this channel estimated? How is the channel estimation done at the receiver? So, let us ask. So, the question is, how is the channel estimated at the receiver? And the answer to that question is by using what are known as training or pilot symbols. So, channel estimation has to be carried out the receiver. As we know, this is a critical aspect. How is the channel estimation carried out the receiver? We employed a training. We train the receiver to give it the measure estimate of the channel. These are known as training or pilot. Pilots are something that are transmitted in front of the actual thing. So, pilot symbols are symbols that are transmitted in front of the information symbols, that is before transmission of the information symbols. These are employed essentially to estimate the channel at the receiver. Let me give you an example. For instance, let us look at this example. In a GSM system, let us consider the example of 2G GSM, because it is very popular. In 2G GSM, every symbol, every frame, there is a frame for a user, for every, there is a slot for every user. Every slot consists of 156 symbols. Every slot consists of 156 symbols, out of which 26 symbols, that is 26. This is the set of 26 symbols which constitute the training symbols. These are the training. In fact, this is in the middle of the slot. If anything is in the front of something of the slot of something, it is known as a preamble. If it is in the middle, it is known as a mid-amble. So, this is also colloquially or technically or even referred to as a mid-amble. So, what I am saying is that GSM, for every 156 symbols of a user, there are 26 symbols that are transmitted in the middle, which is known as a mid-amble. These are all, this is also the training, and these are known as the training or the pilot symbols. These are used to estimate the channel at the receiver, so that you can use this channel estimate to detect your signal. That is the essential idea. All right. Now, fast versus slow fading. Let us come to, now we introduce the concept of fading. Now, what is, when do we say a channel is fast fading or slow fading? So, is it fading fast or is it fading? So, first it is fading in time. So, is it fast fading or slow fading? The answer to this question is it depends on the velocity and the system. Roughly speaking, a channel, if Tc, the coherence time, is greater than the interval, successive intervals of carrying out channel estimation is greater than the inter channel estimation time, that is, coherence time is greater than the time interval between two channel estimation procedure, then the channel is not changing during one channel estimation procedure. Hence, this channel is this is a slow fading channel. However, if Tc is less than the inter channel estimation time, that is, I have estimated the channel. Let me draw this pictorially. I have estimated the channel, that is, this is the time at which the channel is estimated. My next channel estimation time is Te plus Te 2 Te, but my coherence time is only this much, which is Tc, which is less than the interchannel estimation time, which means by the time I get here, the channel has changed. So, if the channel, if the coherence time, that is the time for which the channel is constant, is less than the interchannel estimation time, then my channel has changed, which means my receiver will be in error, because if I am using it to detect the received signal, but my channel has changed. So, I am using the wrong estimate. So, the channel has changed, but the receiver is still employing the wrong estimate corresponding to this channel estimation time. Hence, this results in errors at receiver. Hence, going back to the previous slide, if Tc is less than the interchannel estimation time, the coherence time is less than the interchannel estimation time, then my channel is fast fading. All right. Remember, we said something like this before in the case of coherence bandwidth. We said if the delay spread is greater than the symbol time, then the channel has intersymbol interference, which causes distortion at the receiver. Similarly, in context of coherence time, if the coherence time is smaller than the interchannel estimation time, that is, the interchannel estimation time is larger than the coherence time, then the channel changes at a very fast rate, at a rate that is faster than the rate at which you measure the channel. Hence, it causes errors when you use this erroneous estimate of the channel at the receiver for detection of the symbols. So, that is the essential idea here of coherence time, and that is the importance of coherence time. Now, let us put all these ideas together and formulate a comprehensive picture about the nature of the wireless channel. So, let me draw a comprehensive picture. A comprehensive picture can be drawn as follows. Let us say I am plotting the delay spread sigma tau here. This is the delay spread, and here on this axis I am plotting the coherence time, I will divide this into 4 quadrant. Now, for very high delay spread, the delay spread becomes greater than the symbol time. So, this channel becomes frequency selective. Similarly, here it is also frequency selective. So, very high delay spread, the channel is frequency selective. For low delay spread, the channel is flat fading. That is, irrespective of the coherence time, in low delay spread the channel is flat fading, in high delay spread the channel is frequency selective. Now, let us look at what happens at high coherence time. If the coherence time is high, then the channel is varying at a slow rate, hence the channel is slow fading. Here also the channel is slow fading irrespective of the delay spread. Similarly, if coherence time is low, then the channel is varying at a very fast rate. So, irrespective of the delay spread, it is fast fading, and this is fast fading. Also, if the delay spread is large, it results in intersymbol interference. Intersymbol interference, here there is no ISI, no ISI. So, now we have a comprehensive picture. For instance, let us look at this quadrant. In this quadrant, the delay spread is high, but the coherence time is low, hence the channel is frequency selective. It has intersymbol, results in intersymbol interference, and it is fast fading because the coherence time is low. Look at this quadrant. In this quadrant, the delay spread is low, but the coherence time is high, which means no intersymbol interference, the channel is fast fading, and it is slow fading because the coherence time is high. So, that this picture sort of gives you a comprehensive idea of different aspects of the wireless channel, and this understanding, this clarity of understanding about the nature of the wireless channel is extremely important to understand different aspects of the 3G, 4G wireless communication systems. Let us now go to one final aspect in this channel characterization, which is that of under spread. This is under spread wireless channel. If we looked before, we said the delay spread of an outdoor wireless channel is approximately of the order of microsecond, and the coherence time is approximately of the order of millisecond. Look at this, we looked at both the delay spread of outdoor channels and the coherence time. We said the delay spread is typically of the order of microseconds and the coherence time is typically of the order of milliseconds, which implies that in a typical channel, in a typical channel, the delay spread sigma tau is much smaller than the coherence time. So, in a typical wireless channel, the delay spread sigma tau, which is of the order of microseconds, is about 1000 times smaller than the coherence time, which is of the order of milliseconds. This property, channels that satisfy this property, channels that satisfy delay spread much smaller than coherence time, channels that satisfy this property have a special name. They are known as under spread channels that satisfy the property that the delay spread is much less than the coherence time are known as under spread channel. All right. So, this is the last idea, and all typical wireless channels outdoor, indoor are underspread channels. So, this is the last idea with which we will conclude this section on channels. Let me revise again, let me again list what topics we have covered in this context. In this section we have covered topics such as, so list of topics that is covered. So, let me write summary. In summary, the list of topics that we have covered is first the RMS delay spread. We said this is the interval over which the signal power is arriving. We have covered concept of coherence, bandwidth, which is BC. We have covered ISI, which is inter-symbol interference. We have covered frequency. We said that if the delay spread is greater than the symbol time, it results in inter-symbol interference, and in frequency domain it means that the signal bandwidth is greater than the coherence bandwidth. So, we considered the concept of, we looked at the concept of flat versus frequency selective fading. Then we introduced the notion of the Doppler shift arising from a velocity. If a mobile is moving towards or away from the base station, we said that results in a Doppler frequency shift. We said this in turn results in something important. This is a time varying channel. We said this results in a time varying channel. All right. Hence, what becomes important is what we considered next is the notion of coherence time Tc. This is the approximate time for which the channel can be assumed to be constant. It changes from coherence time to coherence time, which means you have to periodically, every coherence time you have to do channel estimation. Then we looked at the Doppler spectrum and the Doppler spread, and then we also looked at, finally the last concept today, we looked at underspread that is channels whose delay spread is much smaller than the coherence time are known as underspread channels. These are the topics that we looked at today. This completes our second model on understanding the properties of the wireless channel, characterization of the properties of the wireless channel. Hence, now we will go on to the third module of this course on 3G or 4G wireless communications, which is the module on code division for multiple access. So, now let us start the third module. This is the module on CDMA, which also stands for code division for multiple CDMA stands for code division for multiple access. All right, CDMA is a very important physical layer technology or important technology for third generation 3G and third generation wireless communication systems. In fact, I urge you to revise the earlier or recollect the first lecture, very first lecture we did in this course on 3G, 4G wireless communication systems. We said 3G systems are all based on CDMA, namely we said WCDMA, all right, and HSDPA / HSUPA, and also CDMA 2000, 1X EVDO, and so on and so forth. All these are based on CDMA. Hence, CDMA is a key technology. As the name implies, CDMA is a multiple access technology. It's, remember, CDMA stands for code division for multiple access. Hence, CDMA is a multiple access this notion is an important notion. What is a multiple access technology? So, with this, because of short this point, I will conclude this lecture. All right, we will start with a discussion, introduction to CDMA and analyzing CDMA or code division for multiple access in detail starting in the next lecture. Thank you for your attention.